Hello and welcome back to our review for the Chem 4 final. This video is concepts for equilibrium charts that involve weak acids or weak bases. We just covered strong acids, strong bases. Now we're going to cover weak. And now you'll start to see why it's so important that you identify whether something's an acid, base, or salt, video on that, and whether it's strong or weak, video on that. So, the difference between a strong and a weak when you're calculating pH is that weak acid or weak base require an ice chart or equilibrium chart, and they also require an equilibrium constant K. So let's ask our two questions about this reaction. Is it an acid, base, or salt? Remember, this is an organic acid, this is our tricky one, and it's the most commonly used weak acid in Chem 3, Chem 4, because it's tricky. The acidic hydrogen is at the end, not at the beginning, like HCl, HBr. So, second question. Now that we know it's an acid, is it strong or weak? It's not in our strong acid song. HNO3 and HBr, H2SO4. HCl, O2, O4 say high strong acids all. If it's not in the strong acid song, it's weak. So now we know this is a weak acid. We need an ice chart and an equilibrium constant K. Remember, whenever you do an equilibrium problem, ice, K, solve, check, make sure you got the right answer to the question, and SUN. So let's start with our ice chart. Weak acid means that this acid does not let go easily of that acid hydrogen. So what we have is that most of the compounds are going to be these two, not these two. They don't dissociate easily. So we're going to have a very small K. Remember, K is products over reactants. So if we have very little product in the numerator and more in the denominator, that's going to put our K less than 1. So let's ICE. Remember, I stood for the initial concentration that they give you at the start. Oh, there's that L. Remember, there is no S or L. There are no S or L compounds in a K or a chart. So I'm just going to go ahead and cross water out. You can't have a concentration of water, people. And again, since it's the I, the initial, and the problem does not give us concentrations here. Oh, I'm sorry. I left this out. Now this is an acid, so in this equation, water is the base. So acid always gives away its hydrogen to the base. So this becomes CH3COO neg, and the water's gaining a hydrogen, so instead of H2O, it's H3O plus. But we don't ever use H3O plus because that's going to split into water and a hydrogen ion anyway, so we always represent it that way. Okay, so we've started our reaction. We have a starting value here, and since it's the very start of the reaction, we have 0 concentrations there. Remember, we always, for change in the ICE, use the letter X times the coefficient. Well, all of our coefficients are 1, so we're not going to worry about that. Since we're starting with all this, we can only go down from our starting value. So you always subtract the X from the start concentration, and you're going to add the X's times the coefficients here. So at equilibrium, you're going to be left with the starting value minus X times the coefficient, and here we'll have our 2 X's. Again, since these compounds are weakly dissociating, our K is always going to be less than 1. So what would our K value be for this equation? I'm going to take away everything but the E. The K for this expression, the equilibrium constant, always products at equilibrium over reactant. So our K for this would be x times x, or x squared, over our equilibrium value of the reactant, which is going to be our starting value minus x. And as always, you're probably not going to have to, hopefully not have to solve for x using the quadratic formula. So I'm going to assume we're using approximation method. So in the denominator of your K expression, you're going to go ahead and x out the x, just to simplify solving. For all equilibrium problems, ice, K, solve, check, sun. In my classes, I have students chant that over and over again until they are worked into such a feverish pitch that they never ever forget it. Ice, K, solve, check, sun. When you ask for pH, again, of an acid, you need minus log H plus. And the way we're going to find the H plus concentration in a weak acid is we're going to solve for it using the equilibrium chart, the equilibrium values, and the K expression, which is very different from what we had before. For a weak acid, we're not going to do the molarity times the number of OH groups for the weak base. We're going to have to use the equilibrium chart, values at equilibrium, and again, if it's weak, you need to use those values at equilibrium and the K expression, and you're going to solve for the concentration of the OH. So then POH equals minus log OH. Don't make a mistake. It's got to be POH. And our other memorized formula to convert POH to pH, 14 minus POH. So we're going to do in our next video an example of finding pH of a weak acid. I'll see you then.